Every second, billions of watts of electricity surge through wires above your head. But who, or what, decides where that electricity goes? For over a century, the answer was simple: human operators and mechanical switches. Today, the grid is learning to think for itself. Welcome to the smart grid, the nervous system of modern civilization. In this video, we tear apart every layer of the smart grid, from the transformer on your street to the satellite sensors in orbit. The old grid was built for one direction: power plants push electricity, consumers pull it. The smart grid destroys that logic entirely. It enables two-way energy flow, real-time decision-making, and self-healing circuits. Let's start by understanding what we're dealing with. The scale of this machine is almost incomprehensible. The United States grid alone spans over 450,000 miles of high-voltage transmission lines. That is enough wire to reach the moon and back, nearly twice. Now let's tear this system down, layer by layer, starting at the generation source. Layer 1, generation. Power plants, coal, gas, nuclear, solar, wind, inject electricity into the grid. A single nuclear reactor generates over 1,000 megawatts, enough to power 700,000 homes simultaneously. Layer 2, step-up transformers. Raw generator voltage, around 25,000 volts, is useless for long-distance travel. Step-up transformers boost voltage to 500,000 volts or higher, slashing energy loss across the transmission lines. The physics here is elegant: double the voltage, and energy loss drops by 75%. Layer 3, transmission lines. These massive steel towers carry electricity across hundreds of miles at terrifying voltages. At 500,000 volts, the air around the transmission lines literally glows, a phenomenon called corona discharge. Layer 4, substations. Here, transmission-level voltages are stepped down in regional substations. Inside a substation, circuit breakers, capacitor banks, and disconnect switches form a mechanical orchestra. Layer 5, distribution network. Neighborhood transformers, those gray cylinders on utility poles, step voltage down again to 120 or 240 volts. This is the final mile, the last link between the industrial grid and your kitchen outlet. In a traditional grid, this is where visibility ends. Engineers had almost no real-time data beyond this point. The smart grid changes that by injecting intelligence at every single layer we just described. So how does a grid actually think? It starts with sensors, millions of them. The first technology is the Advanced Metering Infrastructure, or AMI. Smart meters replace the old spinning disk meters with digital devices that report usage every 15 minutes. These smart meters communicate bidirectionally. The utility reads your smart meter, but you can also receive signals back. The second technology is the Phasor Measurement Unit, or PMU, the most critical sensor on the grid. PMUs measure the electrical angle, the phasor, of the grid 120 times per second, synchronized by GPS satellites. If a PMU detects an abnormal phasor angle deviation, it signals an impending grid fault, milliseconds before it cascades. The third technology, SCADA systems, supervisory control and data acquisition. SCADA pulls sensor data from thousands of substations into a central control room, creating a living map of the grid. Now here's where the smart grid truly diverges from anything that came before it. Traditional grids required human operators to manually reroute power during a fault. That process took minutes. A smart grid's automated switching systems detect, isolate, and restore power in under 2 seconds. This self-healing capability uses algorithms that run on topology maps of the distribution network. The algorithm instantly identifies alternate paths around the faulted segment and closes the correct switches automatically. But the intelligence goes deeper than just fault response. The smart grid also forecasts demand. Machine learning models ingest weather data, historical consumption, industrial schedules, and even social events to predict load curves. On the night of a major sporting event, energy demand spikes dramatically at halftime, and the smart grid prepares for it hours in advance. This predictive intelligence allows grid operators to pre-position spinning reserves at the right substations. Now let's talk about the renewable energy problem and why the smart grid is the only solution. Solar panels generate power at noon. Wind turbines generate power in storms. Neither cares about your demand schedule. This mismatch between supply and demand, called intermittency, was a death sentence for traditional grids. The smart grid handles intermittency through three key mechanisms: storage dispatch, demand response, and virtual power plants. Grid-scale battery storage systems, some the size of a city block, absorb excess solar power at noon and release it at peak evening hours. Demand response programs are equally elegant. When grid stress is detected, the smart grid sends signals to enrolled customers. Your smart thermostat, your water heater, your EV charger, all these devices pause or delay briefly to reduce peak load. Collectively, demand response can shave peak demand by 10 to 15%, equivalent to taking hundreds of power plants offline. The virtual power plant, or VPP, is perhaps the most revolutionary concept in modern grid management. A VPP aggregates thousands of small distributed energy resources, rooftop solar panels, home batteries, EV chargers, into one coordinated virtual power plant. A VPP with 50,000 enrolled homes can deliver as much responsive power as a small gas peaker plant, with zero emissions and zero new construction. The communication backbone enabling all of this is the Advanced Energy Management System, or AEMS. AEMS runs optimization algorithms every few seconds, solving a massive mathematical problem: how to balance supply and demand across the entire grid simultaneously. This optimization involves hundreds of thousands of variables: generator outputs, line capacities, transformer ratings, reactive power flows. And it must be solved in near real time, or the grid destabilizes. Modern smart grids also deploy wide area monitoring systems that span entire countries, watching for the early warning signs of a cascading blackout. The infamous 2003 Northeast blackout, which cut power to 55 million people, was triggered by 3 transmission lines sagging into trees in Ohio. A modern smart grid with proper wide area monitoring would have detected that thermal sag and rerouted load before any cascade began. So where's the smart grid being deployed right now, and what does it actually look like in practice? California's grid operator CAISO manages one of the most complex smart grids on Earth, integrating over 30,000 megawatts of solar and wind in real time. On some spring afternoons, California generates more solar power than it can consume, and must export it to neighboring states or curtail generation. This is the famous duck curve, the challenge that makes smart grid storage and demand response absolutely essential. In China, the State Grid Corporation operates the world's largest ultra-high voltage smart grid, spanning over 1.4 million kilometers of lines. China transmits power at 1,100,000 volts, more than twice the standard high voltage used in most countries. The electric vehicle revolution is adding a completely new dimension to smart grid management. By 2030, hundreds of millions of EV batteries will be connected to the grid, representing a staggering distributed storage resource. Vehicle-to-grid, or V2G, technology allows your EV battery to discharge power back into the grid during evening peak hours. You earn money while your EV sits parked, and the grid gains a massive, distributed battery that requires no new mining or construction. But the smart grid is not without its challenges, and the biggest one is cybersecurity. Every sensor, every smart meter, every connected substation is a potential attack surface for a cyber attack. In 2015, a coordinated cyber attack on Ukraine's power grid cut electricity to 230,000 people for hours, the first confirmed grid cyber attack in history. Modern smart grids now deploy zero-trust network architectures and AI-driven intrusion detection to defend against such attacks. The smart grid is not a single technology, it is an ecosystem of sensors, algorithms, communication networks, and automated switches working in concert. Every renewable energy panel installed, every EV battery charged, every smart meter deployed makes the grid smarter, more resilient, and more efficient. The grid is no longer just infrastructure, it is becoming the intelligent platform upon which a clean energy civilization will be built. If you found this breakdown valuable, subscribe, because we're just getting started tearing apart the machines that run the modern world.